Hello students, it's Dr. Sansom and we're going to talk about calorimetry today. We have a bunch of practice problems for you to apply the things that we learned last time and the new things that we're going to learn this time. So we'll begin with a little thought. This is from Frederick Soddy. Heat energy of uniform temperature is the ultimate fate of all energy. The power of sunlight and coal, electric power, water power, winds and tides do the work of the world, and in the end all unite to hasten the merry molecular dance. Our learning objectives today are going to be finishing up learning about those 4 types of heat that we talked about last time. We talked about 2 kinds. Today we're going to talk about 2 kinds, and we're going to do some practice problems. So we're going to be analyzing calorimetric data to find the enthalpy of a reaction, the heat capacity of a substance or the calorimeter, or the initial or final temperature of the system. So any of the variables in that equation, we're going to be able to solve for them. As a reminder, last time we talked about a couple of types of heat. We talked about this first type, Q equals mc delta T, which is when we're heating or cooling a substance. Today we're going to talk about the second type here, which is the calorimeter, using a bomb calorimeter. And last time we talked about N delta H for phase changes, and this time we're going to talk about N delta H for chemical reactions. So all of these 4 types can come into play at any time depending on the situation and what we're doing. So we have to be able to recognize which situations call for which equations. Okay, let's talk about the enthalpy of a reaction. This is sometimes called the heat of a reaction. I try not to say heat of reaction because I think it's misleading, and enthalpy is the correct term. And that's our delta H for the reaction. And this is the energy released per mole of the reaction as written. So for example, if I'm talking about butane, I can write out this reaction. Notice I have 13 halves O2. So it's like sort of being in the middle of balancing, right? But we do that on purpose because it's the enthalpy of combustion for 1 mole. So I've written it for 1 mole of butane, and my delta H of reaction will be negative 2877 kilojoules. But what if I wanted to have whole number coefficients? I multiply by 2. Now my delta H also gets multiplied by 2. So whenever I'm writing my enthalpy of reaction, delta H of reaction, it's going to always be for the reaction the way that I've written it. No matter what those coefficients are, it just gets multiplied if I'm multiplying those coefficients. So it's important that we pay attention to the way the reaction is written. Another way to think about this is that the heat released is going to be proportional to the amount of the reactants consumed. If I burn more stuff, I'm going to get more heat. For these situations, we are always going to use Q equals N delta H. N here has a special meaning, which is the number of moles of reactant divided by its stoichiometric coefficient. Okay, so if I'm talking about butane here, and I'm using my first reaction here, my coefficient is 1. That makes my life easy. I just calculate the number of moles, and then I'm using my delta H for here, negative 2877. If, however, I was using the second one where I have 2 moles of butane, I would need to divide by 2. So I'd calculate my moles of butane, and then I would divide by the stoichiometric coefficient in order to get it per mole. Okay, so N here is the number of moles of reactant divided by its stoichiometric coefficient. This is different than what we saw before, where in a phase change you only have one thing happening, right? So it's always 1 mole. So we didn't worry about that coefficient. Now in a chemical reaction, when we're looking at the energy changes with chemical reactions, we have to worry about the coefficients and the way that that's going to impact the heat that's released. Okay, now the second type that we're learning about today is the heat changes in a bomb calorimeter. Now, you're going to know that it's a bomb calorimeter because whenever you do a problem that's about a bomb calorimeter, they're going to tell you it's a bomb calorimeter. So that makes your life easy. In the bomb calorimeter, we're going to have the bomb, which is like the chamber where the reaction is going to happen. We'll have our sample inside there. We'll have water that's surrounding it, and we'll have a really precise thermometer that's going to be able to measure the change in temperature. Now, The thing that's tricky about a bomb calorimeter is that there's water here, but there's also actually the material of the bomb itself, the reaction chamber. And so instead of calculating those out separately, because this could be made of a variety of things, what we do is for the bomb calorimeter, we measure the heat capacity for the calorimeter. That's going to take into account all of the things that are in there that could possibly get heated up. So this is a constant volume device instead of a constant pressure device, which is different than what we saw before. So that means we're not going to have any P delta V work. Normally, if we have a reaction happening at constant pressure, like the other ones that we saw, MC delta T, then PV work could happen. We're not going to allow that here because it's at a constant volume. And because it's a little bit more complicated here, instead of doing the mass times the specific heat capacity for all of the things that are in there, we just calculate this C cal, and we usually have a big C to say this is the specific heat of the calorimeter. So we use this equation similar to the MC delta T that we used before, except we just have C cal. And the heat that's produced by the reaction is going to be released to the calorimeter, so it will be gained by the calorimeter. And if we add those together, because this is an isolated system, it's going to add up to 0 because of the law of conservation of energy. So whatever's released from the reaction would be gained by the calorimeter. Another way to think of it as these would be equal and opposite. Heat produced by the reaction equals negative heat gained by the calorimeter. I think it's easier to conceptualize when we add these together. We don't have to worry so much about the signs. If we add them together and it equals 0, that's because of the law of conservation of energy. So C cal delta T plus N delta H equals 0. In this instance, this is my heat of the calorimeter. That's my C cal delta T. And then my heat from the reaction is my N delta H. When I add them together, I get 0. Let's do a practice problem here. We're going a little old school with our problem solving today, so we're just going to be working this out on paper. But we have this problem. We have 2.38 grams of benzoic acid. We're burning them in a bomb calorimeter. It makes the temperature of the calorimeter increase by 17.25 degrees Celsius. And they've also given us this information about the chemical reaction that's happening and the delta H for that reaction. So what we're going to want to do here is consider the chemical reaction first. Once we know how much heat is released by the chemical reaction, then we'll know how much heat will be gained by the calorimeter. That'll allow us to solve for C cal delta T. So first, let's talk about the benzoic acid. We have 2.38 grams of benzoic acid, and given our molecular mass, that's 122.12 grams for 1 mole of benzoic acid. That's going to give me 2.38 divided by 122.12, 0.01949 moles of benzoic acid. And I have to do one more step. For my chemical reaction here, remember my N is the number of moles of benzoic acid divided by its stoichiometric coefficient. So I'm going to have 0.01949 moles divided by 2, because the stoichiometric coefficient in the reaction is 2. That's my N. For my Q equals N times delta H. This is going to tell me how many kilojoules I have released from this reaction. So I'm going to get negative 62.91 kilojoules released. That's the amount of heat that's released. Notice it's released because I have that negative sign. Now, if that's how much heat is released, then 62.91 kilojoules is also how much heat should be gained by the calorimeter. So I'm going to change the sign of that. I'm going to make it positive 62.91 because now we're going to start talking about the calorimeter, which is the surroundings. So this heat was lost from the system, and it's going to be gained by the surroundings. That's my Q. That's going to equal C cal times delta T. And the delta T here is 17.25 degrees Celsius. So if I take my 62.9 and I divide by 17.25, I'm going to get my C cal of 3.65 kilojoules per degree Celsius. That's my heat capacity of the calorimeter. Now I want you guys to do a practice problem. I've given you this calorimeter. It increases from 25 degrees to 39.5 degrees. And I want to know how much heat is generated in kilojoules and in calories. Okay, for this problem, we're given some information. We're burning peanuts in a bomb calorimeter. Now, those are going to be two separate things, the burning of the peanuts and the heating up of the bomb calorimeter. They have told us that they want us to solve for how much heat is generated here by the burning of the peanuts. So we don't know what Q is for the burning of the peanuts, but we are going to have information about the bomb calorimeter. They said that the temperature changes from 25.00 degrees Celsius to 39.50 degrees Celsius. And they also told us that the heat capacity of the calorimeter is 7.794 kilojoules per degree Celsius. So I'm going to use my law of conservation of energy. I'm going to have my Q of the reaction plus the Q of the calorimeter, and that's going to add up to 0 because whatever heat is released by the reaction should be gained by the calorimeter. And if another way to do this is that the Q of the reaction equals negative Q of the calorimeter. They're equal and opposite. So I'm going to stick with that, and that's going to be negative C cal delta T. That's my heat for the calorimeter. So Q of the reaction equals negative 7.794 kilojoules per degree Celsius times our delta T, which is 14.50 degrees Celsius. And when we multiply those together, we're going to get negative 113 kilojoules of heat released from the reaction. So that's going to be the heat that was released from burning these peanuts. And we might want to go on and say how much heat was released per gram of peanut or something like that. You're actually going to do that in lab when you do your hungry pyromaniac experiment. There are several ways that these ideas are going to show up. You might be looking at heat generated in a combustion reaction being gained by water. Heat from hot metal dropped in water is gained by water. Two aqueous solutions are reacted together and the heat of the reaction is gained by the water. All of those are possibilities. And the trickiest part of any of these is just figuring out what the heck is going on, breaking it down into its component pieces, and then being able to build up that whole system so that you can look at the system and the surroundings and see all of the places where energy might be either exchanged or converted from one type to another. So I'm going to introduce now this decision-based learning model. In the decision-based learning model, we have several sort of decisions that you're going to make along the way, and it's going to lead you to which equation is appropriate, okay? So when you're using this model, you want to first think about all of the processes that are occurring. We saw that last time in class when we were heating up water from minus 25 to 125 degrees. And so we had 5 different processes that were occurring. And today we've talked about it when we had a reaction happening in the calorimeter and then the heat being gained by the calorimeter. Those are 2 different things, right? So 2 different processes. Then for each process, we're going to work through this model and we're going to identify which is the right equation. And then at the end, we're going to add all the equations up to 0 because of the law of conservation of energy. So What I'm going to do is I'm going to work through a couple of examples, but I want you guys to try working through this. So make sure you keep this slide handy. This is going to be sort of your like cheat sheet for working through this. What I want you to do for each of the problems that's coming up is I want you to not solve the problem, but just figure out what equations you need to use to solve the problem. Okay, so I'm going to go to the first one. I'm going to ask you guys to think about it, and then I'm going to walk through the model to show you how I would think about it. Okay, the first one we've got is a 50-gram block of iron that has an initial temperature of 225 and a 50-gram block of gold that has an initial temperature of 25 degrees are brought into contact with one another. Assuming no heat is lost to the surroundings, what will be the temperature when the two metals reach thermal equilibrium? And then they give us the specific heat capacity for iron and for gold. Okay, so these are the things that I'm thinking here. We have hot iron, we have cold gold. So there's going to be some temperature change in the iron that's going to decrease in temperature, and that thermal energy is going to flow into the gold that's going to cause the gold to increase in temperature, and those are going to happen until we come to the same final temperature. We don't know what that final temperature is. That's what we're going to solve for. But there's two processes that are happening. The iron is cooling down and the gold is heating up. So if I come back to my decision-based learning model, I'm going to start with iron cooling down. I'm going to ask, is this a change in kinetic or potential energy? Now, because the temperature is changing, it's cooling down, I know that that's a change in kinetic energy, because remember, temperature is just a measure of the average kinetic energy. My next question is this a substance or is it a bomb calorimeter? And in this case, it's iron, which means it's a substance. So I'm going to use Q equals MC delta T. So I'm going to have a Q equals MC delta T for my iron. That's the first one. Now I'm going to come back to the top and I'm going to repeat this process for gold. Is this a change in kinetic or potential energy? Again, the gold is going to be heating up, so that's a change in kinetic energy. Is it a substance or bomb calorimeter? It's a substance, it's gold. So I'm going to also use Q equals MC delta T, but this is going to be for the gold. So if I come back to my problem, I can do my Q for my iron and my Q for my gold. They're both going to be MC delta T, and then I can add those up to get 0 because no energy is lost. And I do have the solution worked out for you here. Again, you don't have to do the solution right now, although it's good practice for you, so do it if you want. But the important thing here is that you're able to look at the problem and figure out which equations you want to use. Let's do the next one. So the next one, it says we have a 21.8 gram sample of ethanol is burned in a bomb calorimeter. If the temperature rises from 25 to 62.3, determine the heat capacity of the calorimeter. The molar mass of ethanol is 46.07 grams per mole, and the delta H of combustion for ethanol is negative 1235 kilojoules per mole. Okay, so I've got a sample of ethanol and it's being burned. That's going to be one thing, a chemical reaction. And then I've got a bomb calorimeter and that's going to be heating up. So if I come back to my decision-based learning model, if I start with my ethanol burning, is it going to be a change in kinetic or potential energy? Because it's a chemical reaction and the bonds are being rearranged, that's a change in potential energy. So I'm going to come over to this side. Now, is it a phase change or chemical reaction? It's a chemical reaction. So I'm going to use Q equals N delta H. I just have to remember my N is divided by the stoichiometric coefficient. Now, they gave us the delta H of combustion, which is always for 1 mole. So I don't really have to worry about that, but just a reminder, that's the thing we need to worry about. So that's our ethanol. It's a Q equals N delta H. Coming back to the top, now I have my bomb calorimeter. That's going to be heating up, so it's a change in kinetic energy. And it's a bomb calorimeter, so I'm going to have Q equals C cal delta T. So if I come back to my problem, I'm going to have a Q for my calorimeter, and I'm going to have a Q N delta H for my chemical reaction. I can calculate my number of moles, and then I can do all of these calculations to get the heat capacity to solve for C cal of the calorimeter. Okay, let's do the third problem. A boiler turbine takes about 2,700 grams of water vapor to provide about 1 kilowatt hour of electricity, which is about what it takes to watch 6 episodes of your favorite TV show. How many grams of natural gas or methane has to be burned to vaporize 2,700 grams of water at 100 degrees Celsius? The heat of combustion for methane is negative 802. The heat of vaporization for water is 40.7 kilojoules per mole. Okay, so here I have some water that's going to be vaporizing at 100 degrees. So it doesn't seem like there's anything else going on, just vaporizing. And then we're going to have some methane that's going to be burning. So let's come back to our decision-based learning model. And let's talk about our water that's vaporizing. The water is vaporizing, that's a change in potential energy, and it's a phase change, so I'm going to use Q equals N delta H for my water. And then I have my methane that I'm going to be burning. That's also a change in potential energy, but it's going to be a chemical reaction. So I'm going to use Q equals N delta H, but just for the chemical reaction. So if I come back to my problem, I'm going to have an N delta H for water, and I'm going to have an N delta H for methane. If I add them together, because the heat that's released from the methane is going to be added to the water, they're going to add up to 0. So that is that problem. One more like this for us to work through together. Here, a solution containing 0.03 moles of NaOH dissolved in 100 mils of water is mixed with a solution containing 0.03 moles of HNO3 dissolved in 100 mils of water, all inside a coffee cup calorimeter. If both solutions were initially at 35 degrees Celsius and the temperature increases by 2 degrees Celsius, find the delta H for this neutralization reaction. Assume no heat is lost to the surroundings and that the specific heat of the solution is the same as the specific heat of water. And we've got a balanced chemical equation here. We're trying to find the delta H for that reaction. Okay, now we haven't talked yet about a coffee cup calorimeter, but this is just where you use like a styrofoam container that's insulated from the outside. You'll do a reaction in aqueous solution. So it's a little bit tricky because we're going to separate out, even though these are actually occurring in the same physical space, we're going to separate out the chemical reaction, which will be in this case releasing heat, from the whole solution, the mixture that we have there. That's going to be changing temperature, in this case, raising temperature. We don't remove the mass of the stuff that we've dissolved in it, though, when we separate them out. So like the solution, the second part, the solution, it acts as the surroundings, and the reaction actually takes place in the solution, and so all of that's contained in the same mass that we're going to calculate. Okay. So we have a chemical reaction here, and we have water, essentially the solution, that's heating up. So if we come back to our decision-based learning model, first we have a chemical reaction. That's going to be a change in potential energy. It's a chemical reaction. We get a Q equals N delta H for that. Second, we have water that's going to be heating up, or the solution that's heating up. That's a change in kinetic energy. And we're going to treat it like a substance, Q equals MC delta T. We're going to just make the assumption that it's going to be about the same as water, the specific heat capacity. So we'll have an N delta H for the reaction, and we'll have an MC delta T for the solution. Now, I want you to notice I put in 0.03 moles here for my N. I had 0.03 moles of either one of them, and they were in a 1-to-1 ratio. So I can choose whichever one I want to talk about. If we were getting complicated on you, we would ask you to find the moles of the limiting reactant. And technically, that's what you should use, is the moles of the limiting reactant here. And remember, we would divide by the stoichiometric coefficient. So that's my N delta H for the reaction, and I've got an MC delta T for the solution. Notice the solution is 200 grams because I mixed up the two solutions, and those were added together. Okay. Now, we have a practice problem for you to do on your own. This is the number of 5-pound bags of ice needed to cool 36 aluminum soda cans from 25 degrees to 0 degrees. And I'll pause this video here. Okay, for this problem, we're asked how many 5-pound bags of ice do we need to cool 36 aluminum soda cans from 25 degrees, about room temperature, down to 0 degrees, which would be like the perfect temperature perhaps to consume soda. And we have a lot of information they've given us. The initial temperature of the ice is minus 18 degrees Celsius. The mass of the aluminum in a can is 12.5 grams. And the heat capacity of aluminum is 0.897 joules per gram degree Celsius. The density of soda is about 1 gram per milliliter. I actually forgot something, which is there's 355 milliliters per can. And the heat capacity of the ice, 2.11 joules per gram degree Celsius. Delta H of fusion for the ice is 6.01 kilojoules per mole. Okay, so there's a lot of information. This is what we're going to do, is we're going to think about all of the processes that are going on. So the first thing that we've got to think about is our cans are going to be cooling down, as well as the soda within the cans is going to be cooling down. So we're going to get an MC delta T for our cans. We're going to have an MC delta T for the soda itself. And those are both cooling down, but our ice is going to be heating up, MC delta T for the ice. And some of that ice is probably going to be melting. So this is our ice melting. And it didn't specify whether the ice was allowed to melt or not, so we're going to say it can melt. And we're going to add these up, and when we add them all up, they're going to equal 0. I've got some things that are cooling down and some things that are heating up, or where we're adding energy there. And so when I add them all together, they're going to equal 0. And they've asked us how many bags of ice are we going to need, which is going to translate to the mass of ice. So we're going to be solving for the mass of ice here, but we're going to have a little bit of a tricky because we'll also have the N for ice here. So we're going to have to make sure that those are in the same units. Okay, what we're going to do is attack this one thing at a time. We're starting with our cans. We have 36 cans, and there's 12.5 grams per can. So that's going to give me 450 grams of aluminum. We've got the C, and we've got the delta T. They're starting at 25. They're going to end up at 0. So our M is going to be 450 grams. Our C for aluminum is 0.897 joules per gram degree Celsius. And our delta T is going to be final temperature 0, initial temperature 25, so minus 25 degrees Celsius. That is our MC delta T for the aluminum. If we multiply this all out, we get negative 10,091 joules. I'll leave it in joules for now. We're going to have some other stuff in kilojoules. So we'll probably convert those into joules so that we keep it all the same. So this is for our aluminum. Next, I'm going to do my MC delta T for my soda. Now I have 36 cans, and there's 355 milliliters, and we're going to assume 1 gram per milliliter for our soda. So 36 times 355 gives me 12,780 grams of soda. We're going to do an MC delta T using that mass. C for the soda, we're going to assume is the same as water, which will be 4.184 joules per gram degree Celsius. We're going to multiply by our change in temperature, which again is minus 25 degrees Celsius. So let's do that. And we get minus 1,336,788 joules for our soda. Okay, kilojoules are probably going to be useful here, but we're going to stick with our joules right now. And obviously I am not using the right number of sig figs. We're just keeping all the digits right now. Okay, that's my second thing. So I've got my cans, I've got my soda. Now I need to be concerned with my ice. So we don't know the mass of ice, but we do know the specific heat capacity. And we do know that the change in temperature, it's starting at -18 and ending up at 0. So 0 minus -18 is going to give me 18 degrees Celsius for my temperature change. Now, this is going to be for my ice. And we still have this variable here. So I'm just going to multiply these two guys together. So I'm going to get m times 37.98 joules per gram. That's going to be my ice. Okay, there we go. The fourth thing is we have our ice melting. So now we don't know, we were going to have an N delta H. We know the value of delta H, but we don't know the value of N. And we'd like to keep it in the same variables so that we're going to be solving for M. So I'm going to say if I get the number of moles, that's going to be the mass of ice that I have times 18 grams for 1 mole. And this all together is going to be my number of moles. That's my N. And then I'm going to multiply times my delta H of fusion, which is 6.01 kilojoules per mole. Okay, so I'm going to again multiply these out. So I'm going to have 6.01 divided by 18.01. And I'm going to get M times 0.3337. My moles are going to cancel out, and that's going to be, I'm going to say this is kilojoules per gram. That's going to make me feel better because at least the grams will cancel out and we'll end up with kilojoules. So this is going to be for my ice melting. Okay, now I've got the four things and I'm going to put them together. So I calculated before negative 10,091 joules. That was for my aluminum. Negative 1,336,788 joules. That was for my soda. I've got the mass of ice times 37.98 joules per gram. That was for my ice heating up. And I've got my last one that I calculated here, mass of ice times 0.3337 kilojoules per gram. I'm going to actually change that right now into joules so it matches all the other guys. So 1 kilojoule has 1,000 joules, so this will be the same as 333.7 joules per gram. So we're just going to keep that one. Okay, so now I can add up my joules. So let's do that. Negative 10,091 minus 1,336,788. That's going to give me negative 1,346,879. Again, I'm just keeping all of my sig figs here. We're probably going to end up with 2 or 3 when we're done, but whatever. So that's those two numbers. And then I'm going to factor out my M here. So I've got M in both of these, and that'll be times 37.98 plus 333.7. So that'll be 371.68 joules per gram. This is joules over here. And when I add these together, we're going to get 0. I'm going to move my number over to the other side. So I've got M times 371.68 joules per gram equals positive 1,346,879 joules. I'm going to divide by 371 on both sides. And And I end up with M equals 3624 grams. Okay, that's how much mass of ice I'm gonna need, about 3,600 grams. And they asked me how many 5-pound bags of ice that is. So 3,600 grams, there's 454 grams in 1 pound. So we'll divide by 454 and we're gonna get 7.98 pounds of ice. So if they come in 5-pound bags, we're gonna need 2 bags of ice. Something to keep in mind the next time you're hosting a party and you want your soda to be ice cold, about 2 bags of ice for every 36 cans of soda. Finally, we have our summary for the day. We talked about heat transfer in 4 different situations. I'd like you to write down those 4 situations. What are the 4 situations? Which equation do you use? And when would you know, or what would you see in a problem that would tell you that's the situation that we're talking about? So the first one I'm going to write down is my Q equals MC delta T. And this is one that we use when we have a substance or a solution that is heating up or cooling down. Like, for example, if we're changing the temperature of water from 0 degrees to 100 degrees, we're heating it up. This is going to be MC delta T, what we use. Second one, this is when we have a bomb calorimeter, C-cal delta T. And we'll know to use that because whenever we're using a bomb calorimeter, they always tell us it's a bomb calorimeter. Number 3, we've got a Q equals N delta H for phase changes. This one's pretty straightforward, just depends how much stuff we have, how much heat we're going to have to add in order to break those intermolecular forces. And the fourth one is also Q equals N delta H, but this time it's the number of moles of the limiting reactant divided by its stoichiometric coefficient. In order to find my N. So very similar, we're just going to find the moles, but we need to be aware now because of the chemical reaction, we can have stoichiometric coefficients that are going to mess things up a little bit. So this is for chemical reactions. Those are the 4 types of heat that we've learned how to deal with so far. We also talked about the law of conservation of energy. What is the law? How do we use it when solving problems? Conservation of energy just is going to mean energy can't be created or destroyed. And in our case, when we're talking about the system and the surroundings, if I have heat released from the system, it goes into the surroundings, and vice versa. If heat is absorbed by the system, it comes from the surroundings. So if we add up all of the energy changes that are happening, then we should be able to add them up and they would equal 0 because no heat is gained or lost net. It's conserved. That is the end of our lecture for today. Thanks for listening,